Good day, everyone. Before we proceed to our topic, imperfections of solids, I would like to ask some few questions related to it. So first is, what comes to your mind if we say imperfections? So in simple word, imperfections makes us and things around us to be not perfect. So what makes us to be imperfect? So for us humans, it is our mistakes and flaws. But things around us, such as solids, it is defects, dislocation, and impurities. This kind of imperfections will be tackled and discussed in our topic. So let's proceed to our topic. So I'm Joshua Jeremiah Albentonon, together with my groupmate Princess Bea S. Assis. Together we will discuss the Chapter 4, Imperfections of Solids.
For the chapter objectives, number 1, describe both vacancy and soft interstitial crystalline defects. Number 2, calculate the equilibrium number of vacancies in a material at some specified temperature given the relevant constants. 3. Name the two types of solid solutions and provide a brief written definition and/or a schematic sketch of each. Number 4. Given the masses and atomic weights of two or more elements in a metal alloy, calculate the weight percent and atom percent for each element. Number 5. For each of edge, screw, and mix dislocations, A. Describe and make a drawing of the dislocation. B. Note the location of the dislocation line. And C. Indicate the direction along which the dislocation line extends. And lastly, describe the atomic structure within the vicinity of A grain boundary, and B, a twin boundary. 4.1 Imperfections. When we say imperfections, we have this misconception pagdating sa word na ito. Lagi nating naiisip na kadugtong ng word na imperfection is weakness or kahinaan, na kapag may diferensya ang isang bagay is wala ng kwenta. However, as humans, this kind of mindset is laging nadidebunk kasi ika nga ng society, nobody is perfect. Na ang mga diferensya natin bilang tao, that what makes us unique or amazing. And that idea is pwede natin siyang i-apply sa mga materials, specifically solid materials, which is yan ang magiging topic natin ngayong araw. Crystalline defects. Crystalline defects refers to a lattice irregularity having one or more of its dimension on the order of an atomic diameter. A crystalline defects, or sa madaling sabi, na ang crystalline defects daw, ito yung mga imperfections or irregularity in the arrangement of atoms within a lattice. Yung lattice is parang pattern or grid na bumubuo sa structure ng isang bagay. Katulad na lamang ng isang tray ng itlog. Let's say na yung itlog doon, that is the representation of an atom. Habang ang pagkakaayos naman ng mga itlog sa tray ay ang tinatawag natin na lattice. So, kapag nagkaroon ng imperfections sa mga itlog, yung mga imperfections na ito is very small lang. Like, first, sa isang tray may nawawalang isang itlog. And, syempre, sa nawawalang itlog na yun is magkakaroon ng space. And that is an imperfection. Second naman is, kapag may isang itlog na kahit puno na ang isang tray, ay pinipilit niya pa rin squeeze in yung sarili niya. Imperfection din yon. And those small imperfection can alter the material strength, conductivity, or other important properties na may malaking impact sa performance ng isang material sa various application. There are 3 classifications of crystalline defect. The first one is the point defects. Second, linear defects or dislocations. Third is interfacial defects or boundaries. We will explore these 3 classifications in greater detail as we continue with our report. But first, let's start with the first one. The point defects. The point defects are those associated with one or two atomic position. Ang point defects daw are a specific type of a crystalline defect. Ito yung may mga small errors that occur in only one or two specific places. And yung mga errors na ito can be, the first one is vacancies or vacant lattice sites. Ito yung mga sinasabi ko kanina na kapag may nawawalang itlog sa isang tray, magkakaroon ng vacancies sa tray na yon. And the second one is self-interstitial. Ito naman yung kapag may isang itlog na pinipilit na i-insert yung sarili nila sa tray na hindi naman sila nabibilong. And these point defects might seem small, but they have a big impact sa kung paano gumalaw or ang structure ng isang materials.
4.2 Vacancies versus self-interstitials. So, vacancies or vacant lattice sites, the simplest point of defects, refers to the missing atoms or vacant atomic sites. So, basically, there is a vacancies is pakante lang siya guys, like kulang siya na atom. Amo lang ito ang ginamin dire, like kunwari dire sa illustration, ginapakita dire na may kulang na atom sa structure sang atoms sang solids. Kaya siya ginatawag na vacancy since vacant, kulang siya. So, the equilibrium number of vacancies depends on the temperature according to this equation. So, the number of vacancies is equals to the number of atomic sites multiplied by the negative energy required to formulate a vacancy over gas multiplied by temperature in Kelvin. So, self-interstitial. So, in an atom from the crystal that is crowded into an interstitial site, a small void space that under ordinary circumstances is not occupied. So, ginamin lang din sa self-interstitial guys is sobra na atom since 'di ba sa vacancies is kulang, din naman sa self-interstitial is sobra. Like abnormal siya or irregular siya na atom na hindi dapat nag-exist sa site na. Like dire sa illustration na shows dire sa gilid sa left side, dire ginapakita ang kung diin nakalocate ang self-interstitial sa composition sang atoms sang solid. So nakita natin guys na sobra siya sa ang atom na hindi dapat siya nag-exist dira. Like irregular siya na atom. So next is in metals, a self-interstitial introduces relatively large distortions in the surrounding lattice because the atom is substantially larger than interstitial position in which it is situated.
4.3 Impurities and solids. When we say impurities and solids, it is something foreign that is not supposed to be there. Example, sa isang pure at malinis na tubig, kapag nalagyan ito ng dumi, that dumi causes impurity. Similarly sa solids, ang mga impurities na ito yung mga substances that are mixed or nahahalo kahit hindi naman dapat sila nabibilong doon. And ang mga impurity na ito is nakaka-affect sa properties ng isang material. One of the example of a impurities in solid is an alloy. An alloy is a metallic substance that is composed of two or more elements. Alloying is used in metals to improve the mechanical strength and corrosion resistance. As we all know that a metal is already strong, diba? Individually, it is already strong. So, how much more pa kaya kapag pinaghalo pa natin ito sa iba pang mga metal? In that case, ang pag-o-optimize sa mga metal is very helpful talaga in providing sa mas matibay at angkop na material sa mga bagay-bagay. One of the example of an alloy is a bronze, which is it composed of 79 to 95% of copper and 5 to 22% of tin. So yung mga nandiyan sa picture is yan yung mga example ng alloy. Next is several terms relating to impurities. First is the solvent. Solvent is the element or compound that is present in the greatest amount. Kaya nasasabi na ang solvent daw is present in greatest amount. That is because it is the main thing or mas marami na naroroon ito sa isang mixture. Kaya nga 'di ba kapag nagtitimpla tayo ng juice, mas marami ang tubig compare sa juice powder. Also, on occasions, solvent atoms are also called host atoms. Host atoms kasi, yung concept kasi ng host atoms is ito yung nagpro-provide ng environment para ma-accommodate yung mga substances na madidissolve. And dahil nga na main player si solvent, kaya niya mag-provide nito kagaya na lamang kung paano nakapag-provide ng space ang water para ma-dissolve yung juice powder na sinasabi ko kanina. Next term is a solute. Solute is used to denote an element or compound present in a minor concentration. Kung ang solvent is yung mas marami at ang nagpro-provide ng space, ang solute naman is ito yung mas maliit at ito yung dinidissolve sa space na pinoprovide ng solvent. Kagaya na lamang ng juice powder na tinutunaw sa water. Solid solutions is addition of impurity atoms to a metal. It may form when impurity atoms are added to a solid, in which case the original structure is retained and no new phases are formed. Take note the phrase retained and no new phases are formed. Kasi makonsider mo itong solid solution kapag ang isang impurity atom is na-mix sa isang solid, and then it fits perfectly to the point that hindi man lang na-mess up yung old structure or di kaya nag-create ng panibagong structure. Para kang may dinagdag na panibagong ingredient sa niluluto mo and hindi man lang ito nakaapekto sa overall na lasa. Mananatili pa rin itong intact kahit may panibago ng nakahalo. Next is two types of impurity point defects that are found in solid solution. The first one is substitutional and the second one is interstitial. Substitutional. Substitutional is solute or impurity atoms replace or substitute for the host atom. Example is copper and nickel. In substitutional solid solution, sinasubstitute or pinapalitan ng solute atoms ang host atoms. Bale, ino-occupy nito ang lattice sites na normally host atoms ang naroroon. Typically kasi magka-same size ang host at solute atoms. Kaya kapag may substitution na nangyayari is walang masyadong disruption and still considered part pa rin ito ng overall solid solution. Kaya kung makikita mo dyan sa may picture, yung host atom is yung green, the solvent metal atom, and yung solute naman na sinubstitute sa host atom is yan yung color blue. Yung limang blue dyan, yan yung solid element atom. So, pinalitan talaga nila yung space na para dapat sa para sa host atom. Next is a high degree of substitutional solid solubility of one atom type in another is possible when the Hume-Rothery rules are obeyed. Ang Hume-Rothery rules kasi ang magsisilbing gabay para ma-predict whether ang two elements is compatible to form a solid solution when mixed together. The first is the atomic size factor. Dapat compatible yung atomic size ng dalawang solid solution. Second is the crystal structure. Third is electronegativity factor. And fourth is the valences. The second type of a solid solution is the interstitial. Interstitial form for relatively small impurity atoms that occupy interstitial sites among the host atoms. Impurity atoms fill the voids or interstices among the host atom. Kung sa substitution is pinapalitan talaga nila yung host atom, dito naman sa interstitial is pinifill in nila yung mga small gaps sa lattice sites. Kaya nga, kung makikita nyo dyan sa picture, yung mga solute atoms or yung blue is nagsusumiksik sa mga spaces or yung mga void in between sa mga host atom. Yung mga blue dyan, kung kanina sa substitution is pinalitan talaga nila, dyan naman is nagsusumiksik sila na maliliit na parang mga jollen. Next is dito sa picture. Yan yung overall kapag pinakita na yung substitution at the interstitial. Yung lahat ng picture niyan, that is the lattice site na sinasabi ko kanina pa. And yung blue, that is the host atom. Yung green is yung sinubstitute mo or yung solute atom. Habang yung orange naman dyan na mukhang jollen, that is the interstitial impurity atom. For both FCC and BCC crystal structure, there are two types of interstitial sites. But first, let's talk muna what is FCC and BCC crystal structures. FCC is a face-centered cubic, and BCC is a body-centered cubic. These are the two types of arrangement of atoms in a solid materials. The first type of interstitial sites is a tetrahedral. A tetrahedral arrangement is four atoms surround a central atom, forming a pyramid-like shape. This arrangement is common in materials with FCC crystal structure. The next type is a octahedral. An octahedral arrangement is six atoms. Six surrounds a central atom, forming an octahedron shape. This arrangement is common in material in BCC crystal structure. And ito yung kanyang diagram.
4.4 Specification of composition. The most common ways to specify composition are: first, weight percent on the basis of mass fraction. So it refers to the weight of particular element which is related to the overall weight of the alloy. Next is atom percent on the basis of mole or atom fractions. So it refers to the number of mole present on a particular element which is related to the overall number of moles in the alloy. So next, computation of weight percent for a two-element alloy. So, weight percent is denoted as C sub 1 and M sub 1 and N sub 2 is denoted as the weight of element 1 and 2. So, weight percent is equals to weight of element 1 over weight of element 1 plus weight of element 2 times 100. So, times 100 since naka-percentage tayo. Computation of atom percent for a two-element alloy. So, atom percent is denoted as C prime sub 1 and number of moles in element 1 and element 2 is denoted as M sub M1 and N sub M2. So, atom percent is equals to number of moles present in element 1 over number of moles present in element 1 plus number of moles present in element 2 times 100. So, conversions of weight percent to atom percent for a two-element alloy. Since atom percent is denoted as C prime sub 1 and weight percent is denoted as C sub 1 and C sub 2, and atomic weight is denoted as A sub 1 and A sub 2. So, atom percent is equals to weight percent of element 1 multiplied by atomic weight of element 2 over weight percent of element 1 multiplied by atomic weight of element 2 plus weight percent of element 2 multiplied by atomic weight of element 1 times 100. So, same gihapon ang concept sa pag-convert sang weight percent to atom percent sa element 2. So, atom percent of element 2 is equals to weight percent of element 2 multiplied by atomic weight of element 1 over weight percent of element 1 multiplied by atomic weight of element 2 plus weight percent of element 2 multiplied by atomic weight of element 1 times 100. So, baliskad naman. Conversion of atom percent to weight percent for a 2 alloy element. So, C sub 1 is denoted as weight percent and C prime sub 1 is denoted as atom percent, and A sub 1 and A sub 2 is denoted as atomic weight of element 1 and 2. So, C sub 1 weight percent is equals to atom percent multiplied by atomic weight of element 1, and atom percent of element 1 multiplied by atomic weight of element 1 plus atom percent of element 2 multiplied by atomic weight of element 2 times 100. So, same gyapon ang concept sa pag-convert sang atom percent to weight percent sa element 2. So, weight percent of element 2 is equals to atom percent of element 2 multiplied by atomic weight of element 2 over atom percent in element 1 multiplied by atomic weight of element 1 plus atom percent in element 2 multiplied by atomic weight of element 2 multiplied by 100.
4.5 dislocations or linear defects. That is the second classification of a crystalline defect. Dislocation or linear defects is dislocation is a linear or one-dimensional defect around which some of the atoms are misaligned. Dito, nagkakaroon ng displacement from the ideal atomic arrangement. From the term na dislocation, it means may isang atom na namali ang kanyang placement. There are two pure types, the edge and the screw. The edge is a linear defect set on the line that is defined along the end of the extra half plane of an atom. It is called edge because yung dislocation or bump is nangyayari at the edge of a crystal lattice. Kaya rin siya sinasabi dyan na may extra half plane of atom. Kasi kung makikita nyo dito sa picture, ang first line from up to down is punong-puno. Same with the second and the third one. However, the darker blue, which is yung sa middle part, is partially filled lang siya. And diba kung punong-puno is there are 1, 2, 3, 4, 5, 6, 7 na bilog. And yung sa gitna is only 4 lang, which is partially filled. Hindi na puno yung ano. Next is the screw dislocation. Screw dislocation, it derives its name from the spiral or helical path or rump that is traced around the dislocation line by the atomic planes of atoms. It is formed by a shear stress that is applied to produce the distortion show. Screw, same with the word kung paano yung pag-twist sa screw with papunta sa wood. That is also how atoms spiral around sa dislocation line, creating a screw-like pattern. In that diagram, the A, which is yung ito, sa diagram, yung A, which is yung it represents yung sa itaas, yung diagram sa itaas, it represents the screw dislocation, and then yung B is yan yung diagram sa ibaba is ang top-down view ng screw dislocation. Kapag kasi nagkaroon ng force yung atom is nagsaslide past from each other, kaya nagkakaroon ng spiral pattern. So if you look closely dyan sa diagram sa itaas, yung dislocation part or dyan sa dislocation part, yung sa ibaba is gaulbo, habang yung sa itaas naman is kapaatras. So yung spiral motion niya yan is nag-aalaw sila ng stress na nag-aalaw ng stress or deformation without breaking. Mixed dislocations. Mixed dislocation, components of both pure edge and screw are found. Ito yung pinaghalo-halo ng mga edge and screw na dislocation. So, this is the diagram. Kung makikita nyo, dyan sa right part, merong nangyaring edge dislocation kasi nagkaroon ng merong partially filled na And habang sa kabila naman is same with the diagram na pinakita ko kanina sa screw is meron din dyan. And then yung sa baba, that is the top view para sa yung dalawang dislocation na yan. Next is the Verger's vectors. The magnitude and direction of lattice distortion associated with a dislocation. Even though a dislocation changes direction and nature within a crystal, example from edge to mix to screw, the Verger's vector is the same at all points along its line. So when a dislocation moves through a crystal lattice, it causes atoms to shift from the original position. So yung Verger's vector dito, it tells us how much and in which direction these atoms move. So yun yung main trabaho ng Verger's vector. Next is relative orientations of a Verger's vector. The first one is the relative orientation of Verger's vector and dislocation line are perpendicular for edge, parallel for screw, and neither perpendicular nor parallel for mixed. 4.6 Interfacial defects. For interfacial defects is the third classification of crystalline defect. Interfacial defects are boundaries that have two dimensions and normally separate regions of the materials that have different crystal structures and or crystallographic orientation. So for example, let's say that nagkaroon ng contact between water and oil. When they touch each other, yung area kung saan sila nag-meet is called interface. It's like a border or boundary. Diyan sa border na yan, that's where cool stuff happens, like how hindi nagmi-mix ang oil and water, and kung paano naman na using soap can help the mix. Yung boundary na ito could exist between a liquid and a solid or two solid materials. So these imperfections include external surfaces, grain boundaries, phase boundaries, and twin boundaries. And lastly, stacking faults.
So, external surfaces. Surface atoms are not bounded to the maximum number of nearest neighbors and are therefore in a higher energy state than the atoms at interior positions. So, upon surfacing the web and sa libro guys, wala akong makita sang actual na figure or representation sang external surfaces, but ang concept niya is ang external surfaces ay hindi siya rigid or solid as sa interior na composition niya. So, ang ginamin sini is dali lang siya ma-disalign or dislocate and ma-misalign.
Grain boundaries. Grain boundaries is the boundary separating two small grains or crystals having different crystallographic orientations in polycrystalline materials. So, if you would look closely in a block of metal, you'd see that it's made up of lots of tiny pieces like grains of sand stacked together. Now, kapag nag-meet yung mga grains na ito na yung borderline called grain boundary. In the diagram, sa diagram na ito, you would see na may makikita ka dyan na small angle and high angle boundaries. Ang high angle occurs when adjacent grains are significantly misaligned. However, sa small angle naman is slightly misaligned, making it mas maliit ang tilt ng atomic plane sa small angle compared sa high angle.
So, various degrees of crystallographic misalignment between adjacent grains are: first is small or low angle grain boundary. When this orientation mismatch is slight, on the order of a few degrees. So, ginamin dere guys is ang misalignment nila is minimal lang and gamay lang gid kaayo, so di siya ginabaliwala lang siya or Di siya mapansin and di siya ginabig deal. So, next is ang tilt boundary. So, one simple angle grain boundary is formed when edge dislocations are aligned. So, tawag na siya is as tilt boundary if ang edge dislocation niya is aligned together. So, mas ma-appreciate nato na siya if makita natin ang figure na nag-represent sa iya. So, next slide. So, ang twist boundary is when the angle of this orientation is parallel to the boundary. So, ang ginamit sa boundary is yung original na mga points na if iparallel natin siya sa sarili niya, ma-create tas ang twist boundary or twin boundary. So, next slide. Various degrees of crystallographic misalignment between adjacent grains are: first is sa figure 4.9. So, dari na tong tilt boundary. So, ang tilt boundary, so, di ba, ang tilt boundary is, kuan siya, like, alignment of edge dislocation. So, ang edge dislocation diri is gonna represent as ng reverse T na lines. So, makita naton ang top and ang bottom na edge dislocation is naka-align and ang middle na edge dislocation is slightly misaligned. So, sa figure 4.10 is gina-represent niya ang twist boundary. So, makita natin ang sa left side is ang original na boundary. So, ang sa left side na mga points is gina-replicate or giniparallel lang sa isa't isa. So, ma-create siya ng twist boundary or twin boundary.
Phase boundaries. It exists in multi-phase materials in which a different phase exists on each side of the boundary. Phase boundaries play an important role in determining the mechanical characteristics of some multi-phase metal alloys. Sa phase boundaries, it is a border between different states of matter within a substance. So imagine na meron tayong material that can exist in two different forms, like water, na pwedeng maging solid or liquid. Yung area na kung saan ang solid and liquid form ng water nag-meet is yun yung phase boundary. It is very important kasi it marks where one phase ends and another begins. And this is the types of phase boundaries. The coherent phase boundary, partially coherent phase boundary, and incoherent phase boundary. Sa coherent, kung makikita nyo sa picture, ito, yung atomic arrangement niya is aligned. Same yung crystallographic orientation nilang lahat. However, sa partially incoherent naman is this is a so-so, mayroon ng misalignment dito. Sa incoherent naman is walang continuity at alignment at all.
So, twin boundaries. A twin boundary, atoms on the one side reside in a mirror image position of atoms on the other side. So, it means na ina-mirror niya lang or if mag-apply tas ang stress sa isang side, ma-mirror niya ang sarili niya. So, next slide. Twinning or twin boundary. So, if mag-apply tas ang stress sa figure number A, so ma-create tas ang twin boundary. So, as we can see sa figure B, nag-apply tas ang stress sa figure A, so ma-create tas ang figure B, which is nag-represent sa twinning or twin boundaries.
4.9 The basic concepts of microscopy. Microstructure. Microstructure of a material consists of defects and structural elements that are of microscopic dimensions. Take note that grain size and shape are the only two features of a microstructure. Sa microstructure, ito yung arrangement and organization ng small-scale components within a material or substance. It includes features such as grain boundaries, phase boundaries, and yung distribution ng defects. Next is microscopy. Microscopy is the observation of microstructure using some type of microscope. Isa itong scientific technique used to observe and study objects that are too small to be seen with a naked eye. Kaya nga, din itong gamitan ng microscope. And the photograph on which the image is recorded is called photomicrograph. And yung photomicrograph na yun, ito yung example niya. That.
So, 4.10 microscopic techniques. So first is optical microscopy. With optical microscopy, the light microscope is used to study microstructure. Basic components is optical and illumination. So ari ang pinaka-common na technique of microscopic. So since tanan makita alam na ng optical microscopy, ginagamit siya sa microscope, which is ginagamit for the study of microstructure. So next is electron microscopy. It is capable of much higher magnification compared to optical. So it means ang result niya is more detailed and mas complex kaysa sa optical. Ang result niya is more detailed and mas complex kaysa sa result sa optical microscopy. So optical microscopy. So sa figure 4.14, so we can see sa A is polish and etch grains as they might appear when viewed with an optical microscope. So sa section B is taken through these grains showing how the etching characteristic and resulting the surface textures vary from grain to grain because different crystallographic orientation. So sa A is aritong pinaka-simple lang, like makita pag visible. If i-zoom naton, makita naton ang polish and each surfaces niya. So sa C is aritong overall na result sang if i-dikit-dikit naton siya or isahon ang mga grains, different grains is ang makita naton si C, like overall na view sang optical microscopy. So electron microscopy. So we can see na much detailed siya and mas nami ang kuha niya or mas complex kaysa sa optical microscopy. So transmissive and reflective modes are possible for each microscope type. Preference is dictated by the nature of the specimen as well as the structural element or defect to be examined. So depende sa ka-complex sang i-examined. The two types of electron microscopes. First is transmission electron microscope or TEM. An image is formed from an electron beam that, although passing through a specimen, is scattered and or diffracted. 2 is scanning electron microscope or SEM. SEM employs an electron beam that raster scans the specimen surfaces. An image is produced from backscattered or reflective electrons. So ang pinagkaiba ng TEM sa SEM is ang TEM is nagadive deep sa specimen para makafocus sa mga internal structures ng specimen. So ang SEM naman is nagafocus siya sa outer or external surfaces sang specimen. So ang image is gina-produce from a backscatter or reflected electrons. Next is so a scanning probe microscope employs a small and sharp tip probe that raster scan the specimen surfaces. So sa SEM or scanning electron microscope is aring ginagamit niya ang scanning probe microscope para roam around or makagather siya ng data around the surface or outer surface ng specimen. Then, a computer-generated and 3-dimensional image of the surface results having a nanometer resolution.
4.11 Grain Size Determination. A grain size is often determined when the properties of polycrystalline and single-phase materials are under consideration. Each material, the constituent grains have a variety of shapes and a distribution of sizes. There are two common grain size determination techniques. The first one is linear intercept, counting numbers of grain boundary intersections by straight tests line. The second is the comparison, comparing grain structures with standardized charts which are based upon grain areas, such as number of grains per unit area.
So the number of grain boundaries that are intersected by these lines are counted, and the mean intercept length, a measure of grain diameter, is computed using by. So the mean intercept length is equals to the total length of the line over the total number of interception multiplied by magnification. So ari na formula guys is gonna use siya sa line interception. So, ang comparison of pictograph taken at na magnification of times 100 with ASTM, American Society of Testing and Materials. Standard comparison charts may be used to specify grain size in terms of grain size number. So, there is a formula na ni guys is N is denoted as the average of grains per square inch is equals to 2 raised to the power of G, which is denoted as the grain size minus 1. So, ari na formula guys is ginagamit siya sa comparison. Itong na is linear intercept and this time is for comparison. So, for pictograph taken at magnification other than 100 times, use of the following modified form of equation 4.17 is necessary. So, n sub m is denoted as the number of grains per square inch. Then, m is denoted as magnification over 100 squared is equal to 2, and g is denoted as the grain size minus 1. To compute magnification from scale bar, the following procedure may be used. So first is measure the length of the scale bar in millimeters using a ruler. Second, convert the length into microns. Multiply the value in step 1 by 1000 because there are 1000 microns in a millimeter. So 3, magnification m is equals to measured scale length, convert to microns, over the numbers appearing by the scale bar in microns gapon. So that's all for our discussion report about imperfections of solid. So hope you learned something and God bless us all. Thank you for listening.